Now, almost without fail in electricity currents, if we increase the voltage, the current will also increase. And for a wide range of materials, as we increase the voltage, the current increases linearly. So there's a nice linear, in fact proportional relationship between the two. Because of that, we've got this law called Ohm's Law, which says voltage equals current times resistance. Now, in fact, we use this to define resistance for every single object. So we simply say resistance is voltage divided by current. Okay. If this resistance happens to be constant and there's no offset or anything here, then we say the device is ohmic. For other devices, the voltage, we still say it's equal to IR, but R varies depending on the current. Okay? Light bulbs, for example, tend to have a higher resistance when there's more current going through. So these are called non-ohmic devices. Now, they don't really not obey Ohm's law, because Ohm's law is simply the definition of resistance. R is V over I. But these are non-ohmic devices. They don't have a nice linear relationship. For the rest of this chapter, we're going to be focusing on ohmic devices. We often approximate light bulbs as being ohmic. That little demonstration I was using, it treats all light bulbs as if they were ohmic. So we're going to deal with ohmic devices, resistors. Now here we've got a picture of some resistors. These are carbon resistors. They use a little bit of graphite to give varying resistances. And typically in a circuit diagram, they're drawn with a jagged line like this. Because the because the definition of resistance is volts over current, its units are going to be the units of volts, of voltage, which is simply volts, divided by the units of current, which is amps, and we give it its own special name, written with a capital Omega, which is ohms. So the units of resistance are ohms, which are volts per amp.